All right, guys, this is your review test 4 help video for your study guide and preparation for your test. So gave you a couple of handouts here for this that you may find useful. How to find limits at x equals c, and at the bottom, how to find limits at infinity. Whenever you're doing a limit, you will either be approaching a number, which we'll call c, or you'll be approaching an infinity, which will look like this. And depending on which situation you're facing, you'll use one of these different flowcharts. Okay. I will probably reference to this occasionally throughout our video. But basically, you always try direct substitution first technically. That's usually your first go-to. And usually, with most problems, that's not going to work. Usually, if you do direct substitution, you get undefined. And so you have to remove the discontinuity somehow so you can find out what the limit is. So just to kind of help you guys remember what a limit is a value that your function approaches from the left and right. That value doesn't necessarily have to exist. It just has to be the value you're approaching. So if your limit from the left and the right are both approaching the same spot, then the limit exists, and one of these strategies will work. However, there are certain situations where the limit from the left doesn't match the limit from the right, like a jump or vertical asymptotes. In those cases, the limit does not exist. If your limit doesn't exist, then none of these strategies are going to work. And what we have is called a non-removable discontinuity. So the only thing we could do is you could plug in values that are really close to whatever you're plugging in for your limit. You can't plug in that actual number. It'll just give you error. But you could plug in something really close to it. And from there, we can decide whether the answer is positive infinity, negative infinity, or does not exist. But that's for non-removable discontinuities. Okay. As you guys can see, the strategies are broken up based on the type of function you're dealing with. If you have a rational function where you have a polynomial over a polynomial, probably L'Hopital is going to be the best method to go with. If you have any kind of square roots involved in a fraction situation, we're going to do a process called rationalizing. If you have a complex fraction, that means a fraction inside of a fraction, you'll probably just simplify it. If you have ln, more than likely it's a L'Hopital problem. If it's an e function, L'Hopital. If it's a piecewise function or an absolute value function, then you're going to have to find the limit from the left and from the right. Okay, so those are the strategies for removing discontinuities. Let's go ahead and go down here. This is for limits at infinity. Almost all of these are going to involve L'Hopital. Okay, almost all of them are going to be L'Hopital. Even this one over here. Matter of fact, L'Hopital will work on this too all the way through. It's just that there's some shortcuts here based on the exponents. And maybe we'll see that a little bit later. But basically, with limits at infinity, the name of the game is L'Hopital's method. If you don't remember that, you'll definitely remember it by the time we finish this video. Another thing I want to point out to you here is this other little reference sheet I'm providing you with. Now, if you just think about it, a lot of this stuff is kind of, I don't know, in my opinion, pretty intuitive. So, for instance, if you take infinity and you add a number to it, represented by the letter C here, the answer is still infinity. Or if you take infinity and you subtract a number from it, the answer is still infinity. So I'll let you guys look over the rest of these, but they should make some pretty good sense. The only one that I think probably doesn't necessarily make sense, maybe this guy here. Anytime you divide a number by infinity, you're just going to get 0. Okay. With trigonometry, anytime you take a trigonometric function at infinity, it's oscillating, which means it goes up and down. And those limits just don't exist in that case. Now, sometimes you can have a fraction with oscillations in it, okay, like this one. And depending on the situation, it'll either be does not exist or is 0. But once again, I'll let you guys just study that there. Finally, on this reference sheet down here, we have some limit facts about ln and e. It's kind of helpful to keep in mind the shapes of these functions. This is the graph of e. As you can see, the limit at infinity, which means the right side of my graph is going in an upward direction, and so that limit is infinity. But the limit at negative infinity, meaning the left side of my graph, is getting flat against this asymptote, so that equals 0. With similar kind of reasoning, you could see some facts about ln there. And anytime you have a number, it doesn't have to be 1 necessarily, so I could put a c here. But anytime you have a 1 here and you're approaching 0 from the right, it's positive infinity. Anytime you're approaching 0 from the left, the limit's negative infinity. So just some random useful facts about limits and how to use these reference sheets as you're going through this practice worksheet and getting ready for your test. So as usual, I'm going to go ahead and be going over the even problems. So let's go ahead and get started. So on our how to do limits worksheet, technically what you want to do is always try direct substitution first. That means just plug it in. And if you get an answer, then that's the answer. So in this case, the limit is 3. So if you can do just direct substitution, do it. Okay, so that's an example of direct substitution there. Let's go ahead and take a look at number 4. Now, if I were to try to do direct substitution here, I would get 9 minus 3 minus 6 over 0, which is 0 over 0. Now, you may be very tempted to put equal signs here, but just so you guys know, you're not supposed to do that because this is what we call undefined. And that's what that basically means is that this function is not defined at negative 3, so you can't just plug in negative 3 and get your limit answer. Now that doesn't mean all hope is lost. We could just go to our little sheet here and see what to do about that. So let me pull it up real quick here. So we tried direct substitution, that didn't work, so we have to decide what kind of function we're looking at, and it's one of these with a polynomial over polynomial. So you could either factor it or do L'Hopital. I'm going to go ahead and go with the L'Hopital approach, so let's go ahead and check that out. Now L'Hopital, it's important that you remember that L'Hopital only works if direct substitution gives 0 over 0 or infinity over infinity. Okay, so that's the only time L'Hopital works. The good news is that's most of the time. So in this case, when I did direct substitution, I got 0 over 0, which means L'Hopital works. So according to L'Hopital, if you get 0 over 0, that means we can come to the following conclusion. The limit of our function is going to be equal to the limit, that same limit, at a different function. And the different function will be the derivative of the top and bottom. So the derivative of the top is 2x plus 1, and the derivative of the bottom is 1. So that's L'Hopital's little magical move there. If you ever are trying to find a limit by direct substitution, you get 0 over 0 or infinity over infinity, all you have to do is take the derivative of the top and bottom and try to do the limit again, and they will have the same answer. And so in this case, let's try our direct substitution. So if I were to plug in negative 3 now, let's see what I would get. I would get negative 6 plus 1 is negative 5 over 1, which is negative 5. So there's my answer. So that would be the limit. All right. Now it's possible that after you take the derivative, you get 0 over 0 again. So like technically here, when I plugged in negative 3, I could have gotten 0 over 0 again. All that means is try doing L'Hopital again. Sometimes you'll see that it's just never going to stop, and so it's kind of pointless to go that route. but usually it'll eventually terminate and you'll be able to get an answer. Let's go ahead and take a look at this. Now in this one, I would not recommend L'Hopital, but let's go ahead and do our direct substitution first. If you plug in 0, you're going to get 1 over negative 1, which is negative 1 plus 1 over 0, which is 0 over 0. Notice I put my equals there, but that's a no-no because you can't equal something that's undefined. But the good news is we could do L'Hopital technically because it is 0 over 0. But I'm pretty sure you guys would not want to try finding the derivative of this thing. And so I'm going to recommend a different approach to remove the discontinuity. And that's going to come in handy here. Anytime you have a complex fraction, all you're going to do is simplify it. So now that may not seem very helpful, me just telling you to simplify it, but hopefully after I show you this example, it'll help. A while back, we talked about how to simplify these things. The way that we did it was by taking each term and multiplying each term by the denominators. So I've got 3 terms here. And I've got this little denominator here. So what I'm going to do is I'm going to multiply each of these 3 terms by negative 1 plus x. Now you can think of that as over 1 if you want to. And what happens is these will cancel each other out. But since I multiplied this term by negative 1 plus x, I have to multiply all of these by negative 1 plus x. All right, and as a result, we're going to have a different looking limit now. We're going to have the limit as x approaches 0. What's going to be left here now is just a 1. Here, we're going to be left with minus 1 plus x. And here, if we distribute on the bottom, well, actually don't distribute on the bottom here in this case. You'll see why in a minute. We get that. And now what we're going to do is we're going to simplify. So the 1's cancel out. Now I've got x over x times negative 1 plus x. And what happens here is those x's cancel out because they reduce each other away. And that step was very important because now that x on the bottom is what was preventing us from being able to plug 0 into this fraction. But now that we've removed it, that's called a removable discontinuity, now we can do direct substitution and plug our 0 in, and we end up with 1 over negative 1, which is negative 1. So that's how you do the ones that are complex fractions. Okay? Let's go on here to number 8. Direct substitution is going to fail us again here. Like I said, that usually direct substitution does not work. So if I plug in 1 here, I get 1 minus 1, which is 0. If I plug in 1 here, I get 0. So we have 0, 0. Now, you could technically apply L'Hopital to this. Whether or not it would work out, I'm not sure. I've tried it with square roots before, and a lot of times it just kind of keeps repeating and it never really simplifies. So when it comes to these square root ones, I'm recommending a different strategy. Rationalization. So what does that mean? It's been a little while since we've seen it, so I'll show you. You're going to find the part that has the square root in it. And what you're going to do is you're going to multiply that expression by itself, but with a little change. You're going to change the sign in the middle there. Okay. Now sometimes they'll have expressions like this, just so you guys know. And when you multiply that, the one under the root does not change. It's the one between the root and the non-root that changes, just so you guys know. Now our problem doesn't have that, but there are problems that look like that, so I just wanted to make sure you guys were aware of which one to change. But anyway, back to our problem. You multiply this expression on the top by itself, but with this sign opposite. And just to obey the laws of math, whatever you do the top, you have to do the bottom. Now, let's go ahead and simplify this. Now, when you're multiplying 2 binomials that are exactly the same, I'm going to show my work on the side here, but when you're multiplying 2 binomials that are exactly the same, something special happens, so long as they have opposite signs like this. x times x, you do your first times your first, which is going to be square root of x times square root of x is just x. Then you do your outers. Square root of x times 1 is square root of x. Then you do your inners. Square root of x minus there, and then lasts. Now, this is where the special thing happens. Those go away, and you're left with minus 1. Now, in the future, I'm going to encourage you not to actually FOIL it out, because we could do this a lot quicker. Anytime you have a situation where you have two binomials that are exactly the same, one with a minus here, one with a plus here, there is a shortcut you could take instead of FOILing, and that's what I would recommend you use. Here's the shortcut. You just do the first times the first and the last times the last. Same answer, much faster. On the bottom now, I'm not going to actually multiply these ones together. I'm going to leave them separate. That's how a lot of these limit problems work. You're going to be, messing around with one side of the fraction, but the other side you just kind of leave that one alone as it gets changed. And in this case, these are going to cancel out, and that's a removal of a discontinuity there. So now we have a new limit without the x minus 1 on the bottom, and that x minus 1 on the bottom was the reason why we were getting undefined. But now that we have this, we can go ahead and do our direct substitution again, and I get the square root of 1 plus 1 is 2 on the bottom, and then the answer is 1/2 as a result. Okay, so that is the rationalization method. Let's go ahead and move on to number 10. All right, not going to work because I already know that if I plug 0 on the bottom, I have a 0 on the bottom, and that's not allowed. So no direct sub once again. So what can we do? Well, this is a trig function. When it comes to trig functions, I wonder if I put that on my sheet here. I didn't put it on there. But you can make a little note to yourselves. For trig functions, basically, what you're going to do is you're going to do L'Hopital. Okay, so keep that in mind on your little reference sheet. So L'Hopital it is. Now, I didn't really check to make sure L'Hopital was allowed. I know that if I plug 0 on the bottom, I get 0. But what if I plug 0 on the top? Well, that just makes this go away, and you've got cosine of 3 pi over 2. Now, once you got to know your unit circle, some of you guys are taking advantage of that extra credit unit circle quiz I'm giving you. And if that's the case, then this might not be as mysterious to you. But it's sure enough, cosine of 3 pi over 2 is, in fact, 0. So we are good to use L'Hopital here. So let's go ahead and do it. According to L'Hopital's rule, this limit will be equal to a new limit where you take the derivative of the bottom, which is 1, and a derivative of the top. Now, this is going to be a chain rule on the top. I've got my outer function, which is a cosine. And then I've got my inner function here, which is this 3 pi over 2 plus x. Now, the derivative of the outside, the derivative of cosine is negative sine. The inside's going to stay the same. But we do need to multiply it by the derivative of the inside. Now this is just a number, so it's just going to go away when you take the derivative. So all we need now is the derivative of x, which is 1. So multiply that by the derivative of the inside. Now, in this case, my derivative of the inside is just 1, so it's kind of pointless. But I just want you guys to see you will have to do chain rule sometimes, and I wanted to review that with you. All right, so this limit is equal to this limit according to L'Hopital's rule. And therefore, I can now plug 0 in again for x, and I end up with negative sine of 3 pi over 2. And it's just 3 pi over 2 now because this was 0, and 0 plus 3 pi over 2 is 3 pi over 2. We really don't need the times 1 here, and we really don't need the 1 on the bottom either. And if you know your unit circle, sine of 3 pi over 2 is negative 1. So we have negative sine, so that's negative 1, which is 1. So there's our final answer for that one. All right, so moving along. All right, now we're a little bit of a game changer here. We are finding a limit at infinity. And for that, you're going to use the different sheet that I provided you, the second half of that sheet that I provided you with, where it has finding limits at infinity. Now, the one I'm looking at is of this sort. Now, you could just do L'Hopital's rule. Okay, it will work. But there's some nice shortcuts here. Anytime the exponent on the top is less than the exponent on the bottom, the limit's just going to be 0. Or if the exponent on the top is equal to the exponent on the bottom, then the limit is going to be just these coefficients, a fraction of the coefficients, a over b. If n is greater than m, the one on the top is bigger than the one on the bottom, then you have to use L'Hopital. Your answer is going to come out to be some kind of an infinity in that case. Okay, so let's see what we have here. On this particular example, the power on the top is 1 and the power on the bottom is 2. So when the power on the top is smaller than the power on the bottom and you're finding a limit at infinity, the answer is just going to be 0. Now, if you wanted to, you could do L'Hopital, but this is much faster to do it this way, just using that little shortcut. All right, let's go ahead and move on to number 14. In this case, it's the same situation. We're still at infinity, but we do have a difference now. We've got these two numbers are the same. And we saw on our little sheet that anytime the powers match, all you do is you take the coefficient here and the coefficient here, which in this case is a 1, and we don't want to forget about this negative either. The answer is just going to be this 2 over this 1 with that negative in the front. And so the answer is just -2, basically. So anytime the powers are the same, it's just going to be the fraction of the coefficients up front there. All right, let's go ahead and take a look at number 16. Now, in this case, this is one where you have a power that's bigger on the top than on the bottom. And in that case, you are stuck with L'Hopital. So first of all, if you tried plugging in infinity, let's work this out a little bit. Let's just do some direct substitution with infinity. If I do that, I get negative and then 3 times negative infinity squared over 4 times negative infinity minus 1. Now, I'm going to simplify this. We have negative. If you square a negative, it becomes positive. But if you square infinity, you just get infinity. So I have a positive infinity now times 3, which is positive infinity. Let me rewrite this, though. There we go. We do have a negative in the front. But on the top, this 3 times negative infinity squared is just infinity. On the bottom, we have 4 times negative infinity. Now, that's negative infinity. And if you subtract 1 from it, you're left with another negative infinity. Okay. Now, we don't really care about these signs right now, but technically they cancel. And we have infinity over infinity. And that means we've got a L'Hopital problem. I'll abbreviate that LH. So what do we do with L'Hopital? We rewrite the limit, but this time instead what we're going to do is we're going to do the derivatives of the numerator and denominator. I want to forget that negative. The derivative of the top is 6x. The derivative of the bottom is 4. All right. Now let's try doing our direct substitution again. If I plug infinity this time, I get negative and then 6 times negative infinity over 4. Now, 6 times negative infinity is negative infinity. And then 4. In this case, these cancel out. And infinity over 4 is just infinity. Now, if you guys are not, if this isn't making sense to you, like why this is infinity or why this infinity divided by 4 is infinity, then you might want to look at this sheet. Like, for instance, I had 6 times negative infinity. How did I know that was going to be negative infinity? Well, it's right here. A number times negative infinity equals negative infinity. Or how did I know that infinity over 4 equals infinity? Well, because right here we have infinity divided by a number equals infinity. So that's how this sheet can be helpful to you if these operations with infinity aren't obvious to you. So you'll notice on this problem, I did stop once I got to infinity and I was done. Now, just so you guys know, that means the limit doesn't exist. But if you get infinity over infinity, you're not done. You got to keep going and do L'Hopital some more. But as soon as you get something just like infinity or negative infinity or a number, then you're done. Okay, so let's go ahead and move on here, number 18. We have a limit at infinity with ln. If you look at your little chart, you'll see the proper strategy there is L'Hopital. So we're going to plug in here, and you get ln of infinity. Plug in here, you get infinity squared. And this may seem odd to you, but the limit of 1 at infinity is still 1. The reason for that is because if you think of this as a graph, here's a graph, here's 1. The graph of y equals 1 is just a flat line. So as you go to infinity, which means to the right, it's never going to stop being at 1. So no matter how far to the right you go, the limit is always 1. So that's why that's the case there. Let me clear that off real quick. All right, so anyway, back to the problem. Ln of infinity, what is that? I believe that's on our little reference. Right here, ln at infinity equals infinity. So the top is infinity, the bottom is infinity, and then we got our plus 1. So this is an indication that we need to do L'Hopital. All right. So now this 1 is going to remain unaffected this whole time. We're only applying L'Hopital to this piece here, just so you know. So when we start doing our derivatives for L'Hopital, this 1 is not, we're not going to take the derivative of that because this is not part of the L'Hopital situation. This was the one that was infinity over infinity. So that limit is going to be equal to the following limit. The derivative of ln is 1 over x. The derivative of x squared is 2x. And like I said, the 1, we're not going to take the derivative of that because it's not part of the L'Hopital process. All right. Now, let's go ahead and do some direct substitution here. If I plug infinity in here, I get 1 over infinity on the top. And the bottom, if I plug in infinity here, I get infinity there. Now, on our little chart, if you guys look, anytime you have a number over infinity, that is 0. And once again, that applies here now as well. Any number over infinity is 0. And so the answer is 1. Go ahead and take a look at number 20. Whenever you're finding a limit at infinity with an exponential function, it's going to be a L'Hopital situation. So let's go ahead and get started here with this. So actually, I think direct substitution is going to work out here. We'll see. Let's plug it in. We get e to the negative, and then we're replacing the x with negative infinity. And then negative 4 at infinity is still negative 4. That's not going to change. Now in this case here, we have negative infinity, which is infinity. Now what is e to the infinity power? Well, if you look at your little sheet that I gave you, a reference sheet, it's just equal to infinity. And so we've got negative infinity minus 4, which is negative infinity is the answer. So no L'Hopital on this one because direct substitution was able to get us to our answer that we wanted. Okay, let's go ahead and move on to number 22. Got another trig problem here. So when you have trig problems at infinity, it's going to end up being probably a L'Hopital problem. Let's see. Maybe not. We'll see. If I plug in infinity on the bottom, I get infinity. If I plug in infinity here, this is interesting. We'll talk about that in a second. And then infinity for 4 is just 4, right? Now, what is this? What is sine of infinity? When you take the limit of a trig function at infinity, you get an oscillation. That means the graph is going up and down repeatedly. So for our problem here, sine of infinity is just going to give us an oscillation. So we have an oscillation over infinity plus 4. Now, an oscillation over infinity is equal to 0 if that function was a sine or cosine, which it is. So we have 0 plus 4, which is 4. All right. Next problem. All right, let's go ahead and do some direct substitution. We have 2 times negative infinity over cosine of 1 over negative infinity. Now, in our little reference sheet, anytime you have a number over infinity, that's just going to be 0. So this is cosine of 0. And on the top, 2 times negative infinity, that's just negative infinity. Cosine of 0 is 1. And so the answer is going to be negative infinity. Direct substitution, that's all that was required there. All right, let's go ahead and move on to 26. Got ourselves a piecewise function. Now, if your limit is telling you to find the limit from one side or the other, like in this case, there's a little negative here, that means I'm just doing a left-sided limit. Then you only have to do one side of the limit. But if it doesn't have a sign here, then you have to do both sides, okay? So, since this is a negative, that means I'm finding the limit from the left of 0. Now, if I'm to the left of 0, that means I'm less than 0. So I'm going to be plugging this number in here into this function because that's where x is less than 0. If this was a plus, I'd be doing the one on the bottom where x is greater. And so my answer is going to be negative 0 squared minus 2 times 0 minus 1, which is just negative 1, and I'm done. Okay. Let's go ahead and take a look at 28. And just so you guys know, I'll back up a little bit. For 25, for this one, you need to find the limit from both sides because there's not a plus or a minus here. So in that case, you would plug in 3 here, and you would also plug in 3 here. Now, if you don't get the same answer for both, then the limit does not exist. That would mean you have a jump discontinuity. But if they do match, that means that's your answer. That's the limit. But I'll let you guys do that if you're interested. 28. This is what we call a step function. I'll review briefly with you what it is. Basically, what a step function is it is a function that rounds whatever you plug into it, rounds that number down to the nearest integer that is less than or equal to that. So that's kind of a weird sentence, a little bit difficult to understand. So let me give you an example. Suppose you have this step function here, and you plug into it 3.3. What the step function is going to do is it's going to round this number down to the nearest integer, meaning non-decimal or non-fraction number that is lower than it or equal to it. So the integer that is lower than 3.3 is 3. Or if I gave you 3.9, that would still be 3 because we're rounding it down. Okay. Now something kind of funny happens with negatives. So if you plug in a negative 3.3, the integer that is lower than negative 3.3 is actually negative 4. So you got to be careful with that. Think about it on a number line. If here's negative 3, here's negative 4, 3.3 is here. The number that's smaller than that is this way, so it becomes negative 4. Whereas for a positive 3, 3.3 is here, if 4 is here, and so rounding it down takes you to 3. So that's why that happens there. If you ever plug in an actual integer like 5, well, the answer is just that integer, it's 5. So that's what step functions are. And whenever you graph them, you'll see why they're called step functions, because they look like steps. They look like this. Okay. And because of that, as you guys can see, there's going to be some discontinuities. Obviously, like if you were to pick this point, there's going to be a jump discontinuity, and so the limit would not exist. So now, once again, this one's a lot like the piecewise functions. If they put a symbol here, that means you're doing a one-sided limit. You're only doing it from the left side. If they put a plus here, you're only doing it from the right side. Now, just so you guys know, step functions are going to be treated like non-removable discontinuities. So you might want to add that here, step functions. So for step functions, what we're going to do is we're going to treat them like non-removable discontinuities. So what we're going to do is we're going to plug numbers in that are really close to the number we're supposed to be plugging in, and we're going to interpret our answer as either positive infinity, negative infinity, or does not exist. So that's how we're going to handle these ones. So let's see how to do that here. All right, so what am I plugging in here? I want to plug in 3, but I can't plug in, we're not going to plug in 3. What we're going to do is we're going to plug in a number really close to 3 that is to the left of 3. Okay, so why is it to the left? Well, that's because of this little negative here. So how do we plug in a number that's really close to 3? We are going to plug in 3 minus, that'll be to the left, minus a number that's smaller than 3. So let's just say 0.01. Now if I subtract 0.01, that's going to give me 2.99. Okay, so this is what I'm going to plug in here for x. I'm not going to actually plug in 3. I'm going to plug in a number really close to 3 that's to the left of it. And you can do that by just subtracting a small number like 0.01 or 0.001 or 0.1 from 3. So if we plug that in, here's what I get. I get 2.99 minus 1, which is 1.99. And our step function is going to round this down to the nearest integer that is less than or equal to this, which is 1. And so there's my answer there. Okay, so for step functions, we're going to treat it like a non-removable discontinuity. And the way you do that is by plugging in something really close to the original number and then following the rules for step functions after that. All right, let's go ahead and take a look at number 30. Now for this one, if you plug in 2, direct substitution, you're going to end up with 2 over 0. Now, if we get 0 over 0 or infinity over infinity, there's hope. That means we could do L'Hopital or something. But when you get something like this is just a non-removable discontinuity. And the way that you handle that is, like I just showed you in the last problem, is by not plugging in 2, but by plugging in something really, really close to it. Okay. Now, since I've got a minus here, I'm only going to plug in a number that's really close to it on the left. If I had a plus here, then I would plug in a number that's really, really close on the right. So if you want to plug in numbers really close to 2 on the left of it, just put 2 minus and then plug in a really small, or subtract from it a really small number like 0.001. And that gives me 1.9999. Now, just so you guys know, if this was a plus instead, then instead of subtracting 0.0001, you would add 0.001. Okay, but we're going to use this. And at this point, it's just going to be a calculator problem. So get out your calculators and figure out what this is. And when I plug this in, I get negative 500. Now, that doesn't mean that's my answer for this one. What this means is that since I've got a non-removable discontinuity, it's probably going to be an asymptote. Now, we want to find out what's happening at 2. Now, 2 is right here. And what's happening is, as I'm plugging in a number that's really close to 2, but to the left of that, like 1.99 over here, and I get a really negative number, like negative 500, so it's way down here. What that means is that as the graph is approaching my asymptote, it's dropping down this way, and that means that my answer is going to be negative infinity. Okay, so there is that. Now, if you got a positive big number here, then you would say it's positive infinity. So that's how you deal with non-removable discontinuities. All right, and I believe that takes care of our work for the day. So that's limit review for you. Hopefully it was helpful, and we'll see you guys for your review test.